Newton's method for the solution of equations. Let us first plot the x minus 1 squared. And we have the slope here at point B of this red line. This is the slope at x equal to 1. So that is our first approximation. The second approximation is the slope at x sub 2. Okay, so find the root of equation f of x equal to 0. The first approximation of the root of the equation is x1, and the second approximation is x sub 2. The slope f prime of x is given by from the plot from the figure. So BE over C equal to f prime of x. So that is equal to f of x1 over x1 minus x2. The approximate solution of the equation now is x sub 2 equal to x sub 1 minus f of x1 over the slope of f of x at x sub 1. So in general, we have the uh, x sub n plus 1 is equal to x sub n minus f of x all over f prime of x sub n. So we have this this length CE is equal to this is equal to f of x1 over f prime of x1. Okay. So Newton's method, also called the Newton-Raphson method, is an iterative numerical method used to find approximate solution of nonlinear equation of the form f of x equal to 0. The idea behind the method, suppose you want to solve f of x equal to 0, start with an initial guess x sub 0 equal to the close to the true root. Approximate f of x here near x sub 0 by the tangent line at x sub 0, f of x sub 0. The point where this tangent line intersects the x-axis is taken as the next approximation, x sub 1. So repeat the process to improve accuracy here. For example, this is our first approximation here using this formula. So x sub 1 here, that's the first approximation. Then we have the second approximation here, x sub 1 minus f of x sub 1 over f prime of x sub 1. So the formula to be used is x sub n plus 1 is equal to x sub n minus f of x over f prime of x sub n. So where f of x here is the functions, f prime of x is its derivative. X sub n is the current approximation, and x sub n plus 1 is the next approximation. And we have the geometric meaning here. At each step, you do the tangent to the curve y equal to f of x at x sub n. So the x-intercept of this tangent is the next approximation, x sub n plus 1. So x sub n plus 1 here is equal to x sub 2 here. So our x sub n here is equal to x sub 1. So we have an example here, f of x equal to x squared minus 2. So from these functions, we can easily find the root of the equation. So x here is equal to the square root of 2. Then we have the derivative here equal to 2x. So derivative of x squared minus 2 is equal to 2x. So from the formula here, so let's have x sub 0 equal to 1. So substitute in the formula. So 1 minus 1 squared minus 2 over 2 times 1 is equal to 1.5. So that's our next approximation. Then our next approximation is x sub 2. So let's use the previous approximation as our first approximation. So 1.5 minus 1.5 squared minus 2. So from here, 1.5 then all over 2 times 1.5, that is 1.4167. So our next approximation is x sub 3. So let's substitute the x sub 2 in this formula. What we have is 1.4142. So our exact solution here is square root equal to 1.4142. Okay, very fast advantages, very fast convergence if initial guess is close to the root of quadratic convergence. We have the disadvantages here. Requires a derivative. It may fail if f prime of x is equal to 0, or if starting guess is far from the root, or it can diverge. So we have an example here. We can see our first approximation here is equal to 1. Then we have the next slope here at 1.22. Then we have the next slope here, 1.35. So we just substitute here the our approximation 1.0. Then if we substitute that, we can have the next approximation. Then repeat the process until we have the value square root of 2. The approximate value is 1.4142. So we have the simulation by Mathematica. So we use the manipulate here module. So our module is FDF steps, current, tangent lines, roots, and exact roots. So define function and its derivative. So f of x is equal to x squared minus 2. Then we have the derivative here equal to 2x. The Newton's formula here, Newton's step, is x minus f of x over the derivative of f of x. Then we have the steps here. Next list Newton, we have the initial value x sub 0 up to n. So the next list here means we have to repeat the process. We have to repeat for example, from x sub 1 to x sub 2, from x sub 2 to x sub 3. So that is what the next list does. Then calculate the tangent lines for visualization. So our tangent lines here, we have to make a table here where we have the dash lines. And we have the color 97, colorless. So we have to choose which of the colors we have to show. For example, here we have the lines. So this step 1 here is the first approximation. Then f of step 1, step I, is the corresponding y value. Then at x equal to 0, so we have the solution here. We have the root of the equation here, approximate root is equal to steps. The value at the steps of I plus 1. And the corresponding value of y here is equal to 0. Then we have here I is from I equal to 1 to the minimum of this value. That we don't use all the values of the steps here. So it depends upon what value, up to what value of the steps we use. Then we have to subtract 1 here to avoid using all the values in the steps. Then we have the exact root here. The exact root is equal to the square root of 2. Then we have the roots here. We have the two roots here, the exact roots, positive exact roots, and negative exact roots. And then we have to show here the plot. So our plot here is f of x equal to f of x. So our f of x here is equal to x squared minus 2. So we have the values of x here from negative 3 to positive 3. Then we have the plot range here from negative 5 to 10, like this one. So from negative 5 to 10 here. Then plot style here is thick, then axis level x, f of x. So we have x here, x, and f of x here. Then we have the x-axis, x-axis here is equal to x. Then plot level Newton's method for f of x. So we have here Newton's method for f of x equal to x squared minus 2. And for the graphics, we have the red. So we have the red here. So we have to move the red point here. Then we start at x sub 0 and f of x sub 0. These are the initial values of x and y. So we have the blue point here. So the blue point here, the blue point is moving above the x-axis. For example, our approximate first approximation here is this negative 1.7. Then our next approximation is uh, this is negative 1 point, approximately this is 1.34. Now for the positive root here, so our next we have the initial guess here equal to 0 here, x is equal to 0. So our next guess here is x equal to 1. Then our next guess here is this is the root, the approximate value. So this is around this is around 1.43. Then on the other side, this is also negative 1.43 approximately. So we have here. So this is negative 1.33. Negative 1.38. So that is for our red point. Our guess, uh, our guess point here is the red point. So we start at the initial guess here is x sub 0 and f of x sub 0. Then we have the blue points here. The blue points is for the points above the x-axis. For example, here we have the blue points here. Then we have the green points. This is for the approximate solution. That is negative of the square root of 2 and positive of square root of 2. So the values at roots here. So we have the roots square root of 2 and negative square root of 2 here. So the these are the roots of the equations. Then we have the tangent lines here from negative 3 to positive 3. So we have the dash. Then we have the x here initial guess. So we have the initial guess here. So this is our initial guess. X sub 0 and f of x sub 0. So our initial guess here is from 0, x equal to 0. Then we have the exact roots here at y equal to 0. So the root there is exact. Then we have the 0 to here. This is also the initial guess. And we have the epilogue here, inset and panel. And we have a column there. In the column, we write the iteration details here. This one. Initial guess 1.005. So this is 1.005. And iteration is equal to 9 here. So we have the iteration here equal to 9. And we have the number form here. Uh, the total number of digits here is equal to 4. The number of decimal places is equal to 3. So that's why here we have the 4 significant digits or 4 significant figures. We have the 3 decimal places, but we have 4 digits here. So that is what the number form means. Then iteration here refers to the number of iteration is equal to 9. So here, that is 9. Then the current approximation here is equal to 1.4142. So this is current approximation 1.414. So like this one, so 1.442. Then we have the error here. What is the error? Number 4. So this is the uh, approximate value minus the exact value here. So we have the approximate value minus the exact value. So we have the 5. It means this 5 is 5 digits and 4 decimal places. Right. So we have here 4 digits and 4 digits with the 5 uh, significant digits here. So if supposing if this these numbers are not all equal to 0, then we have the exact root here, square root of 2. So the number form, so we have 10 digits with 9 decimal places. So here, the current approximation has uh, 10 digits with 9 decimal places. The background here, light black. So we can see here because the background is light black. So we have the scale 0.75 and 0.8. So this one is located approximately at x equal to 0.75 and y is equal to 0.75 means 75% of the total length of the x-axis, and we have the 80% of the y-axis. So this one, the location of this uh, the location of this control placement. No, the location of this description here of the values. And we have the control elements. So initial guess is our initial guess 1.005. So here, so that is from negative 2.5 to 2.5 here. So we have the values from negative 2.5 to 2.5. So appearance are labeled. Then the number of iteration here is total number of iteration is equal to 10, but we have only here equal to 9 here. So iteration from 1 to 10 and from 10 to 1. So we have the control placement here at the bottom. So this is our control placement. the bottom here. So this is our control placement. And track symbols here, x sub 0 and n. So we have x sub 0 and n here equal to 9. So initialization is equal to null. So there are no values for the initializations.